hypothesis. Okay. The null hypothesis is always in the form H naught is some parameter equal to some specific value. Okay? The alternative hypothesis can take on a different values based on the context. And you can have one-sided alternative hypothesis or you can have two-sided. And we saw that in the warm-up today. Right? All right. The two-sided alternative used if it's equally interested in deviation on either side of the null hypothesis. Kind of like that not equal one we looked at. You have to be careful with the p-value though. You have to evaluate in either direction. And let's draw an example of this. If I do a two-sided hypothesis like this, and here's our null hypothesis, right? Let's say our null hypothesis is that p equals 0.7. The alternative, if I say p is not equal to 0.7, and I do a test and I get something like 0.8 and go through all things and I get somewhere in here, I have to shade in this and this. And the p-value is the sum of those two areas. Because you said, for your alternative, not equal to. So I'm looking for the probability of getting my test statistic result or something more extreme than that in the direction of the alternative hypothesis. And if the alternative hypothesis just says not equal to, then we have to look this way. In both directions. Okay.
Wait, why is everything not shaped except like right there?
Not shaped where?
What are the values?
Why isn't all of this shaded?
Why isn't all shaded? Well, first of all, I'm saying that I put a test statistic in here. Let's say my sample mean. My sample mean was 0.9. Okay? But then, that's not my z-score, is it? I have to take p hat minus p all over the standard deviation of all the possible p hats. And that's what I'm doing. Okay. I could say this is 0.9, and this is again a standard deviation, and it has to be with the answer. We're going to get into specifics later. But see, I'm shading in. This is my test result right here. And I want to figure out, wow, that wasn't 0.7. Is that enough to say, oh, the status quo is wrong? Well, we have to look back now to see what's the chance of getting a 0.9? And it's just a little more sophisticated than saying, what's the probability of getting one sample to be 0.9? If you did that, you'd always just get this little line segment on here, and calc students can tell me what that is. What's the area of the line segment on a continuous curve? 0.
I do that.
You've got to have some stretch, right, to get an area on a continuous curve. So that's why we talk about what's the chance of this or something more extreme happening in both directions.
What's like the value on the other side, though? Like,
These would match.
These be given and
These two would be equal. These are equal areas on either side of 0.7. Okay? We'll come up with specific values in a second here. Notice on the one-sided, you only go in one direction, and that's why it's also called one tail. So if I got my null hypothesis is 0.7, and the alternative, let's say, is p is greater than 0.7. So now when I get my 0.9 result in here, I look at this area. And what's the area of that? And that gives me my p-value. Okay?
why aren't you taking it from the 0.7 over? Why are you doing it from this 0.9? Yeah.
Oh, well, see, I don't have any of the other details yet. Okay, I'm going to take it from the test statistic that I do. Remember, this is just the hypothesis. As is this too, this is the alternative hypothesis. Hypothesis testing is first establishing what is the status quo, what is the old thinking, and then you test it with a specific sample. And so I don't have any more details on there, I just want to give you the general sketch. Where do you get this 0.9 is? From looking at your test statistic. And also, how do I make this curve? I got to make sure I use the right standard deviation of all possible sample proportions. Okay. 54.2? I mean, by chance, it would be 50%, right? Or is this evidence to suggest that there really is a home field advantage? I mean, could that just happen by chance, winning 54% of your games? It's hard to tell. You don't just take a difference in these and say, oh, we're 4.2% over normal. It must be different. You got to look at the sample size and standard deviation and test all your things and so forth. So let's run through the gamut here. When testing the hypothesis, we are asking when the observed rate of home victories is so much greater than 50%, we can't explain it away as just a chance variation. That's just sort of a verbal way of describing what we're going to go into now, the whole hypothesis test. This 54.2 is a test of what we think the hypothesis should be. What do you think the hypothesis should be? What's our null hypothesis here? P equals 0.5. Now, you should really write it out in context. Context. The ratio of home games won in the MLB is 0.5. Give it a little context, and you just grab the context right out of the statement of the problem, right? And once you state the context for the null, it's implied for the alternative as well. What's the alternative in this case? We're trying to show if there's a home field advantage. So we suspect there's an advantage. So you suspect that P is greater than 0.5. Okay. So the model, do we have all these assumptions? The randomization condition. Is this a random subset of all the things? Didn't they take all the games from 2002?
Shouldn't they? Isn't it not random though? They're all from like the same
Random.
year.
It is not a random, simple random sample. It's not a simple random sample. But it is representative. Although you could say in 2002 versus 1922, there might have been some significant changes in how baseball games are played and in the stadiums that they're played in. What's the big difference? The dome. And the home team is probably used to the local weather more than the Florida Marlins or whatever they call those baseball teams in
Miami Marlins.
Miami Marlins. So you have to account for weather. No, but maybe like the Packers are used to playing in snow more, cold weather. That's part of the home field advantage. But now when you enclose a dome or something, it's less of an impact. Right? All right, fine. You think it's a simple random sample? Okay, Jim.
I'm not saying it's
Do we have 10% condition? Now, careful on the 10% condition. Is this less than 10% of all MLB games? I would say yes. Okay, so let's check on that. How about the success-failure condition? Now, notice what you use on the success-failure condition. When we did confidence intervals, all we had was P hat and Q hat. Now, you're assuming this. Since you're assuming that the null hypothesis is true, then we can use 0.5. So how many games were there, folks? Get back in your notes.
24, 25.
How many?
24, 25.
24, 25 times 0.5. And what do you get? And n times q. Notice I'm not using p hat or q hat. Oh, they're both going to be the same, aren't they? Because I'm using 0.5 for each. And you get 12, 12.5. 12, 12.5. Those are both greater than 10. So we have checked out that condition. Okay? Since the assumption the condition is satisfied, we can model the sampling conditions with a normal model and do gotta name the test. That's too general, too big a brush. Narrow it down. No. First of all, how many samples were done? One. So one sample proportion z-test. Okay? All right. Now the mechanics. P naught. 0.5. That basically comes from the null hypothesis is that P equals P naught. In this case, P equals 0.5. Q naught then is also 0.5. The number, I think someone just told me 2425. P hat is 0.542. And for the standard deviation of all the possible P hats, you get the square root of PQ over N. So square root of 0.5 times 0.5 all over 2425. I didn't bring my calculator today. Has anybody got that one?
0.01015.
Okay, and you just stole that off the sheet.
I thought that's what I was supposed to do.
Yes, you are. Okay. But I also want to make sure we know how to do these on the calculator. If you don't, let me know. You can take a pause and we'll calculate a pause break. The z-score then, where does that come from?
0.542 minus 0.5.
Okay, but now I need a formula.
It's the P.
Yeah. You can say P or P naught.
The standard deviation of.
Right. So we get 0.542 minus 0.5 all over 0.0105. And what do you get for your z-score?
How do you know what standard deviation is?
Well, these forms are actually on your formula sheet. On that green sheet you get in your code.
Why would it?
And that's why you name the test too, because then it tells you under one sample proportion, it actually has this formula for you. Now you're saying, which one do you use P hat and Q hat, or do you use P and Q?
Yeah, how do you know like to use 0.5 instead of 0.5?
Good question. You use 0.5 and 0.5 because that is more exact. That is specifically the standard deviation. That standard error we talked about when we were doing confidence intervals, you have to basically, that's less accurate because you're using P hat because you don't know what P is. But in the hypothesis test, you assume you know what P is. And so that's why it makes it a little easier in that respect. That's how hypothesis tests are essentially different than confidence intervals. Because the confidence interval, you don't know anything about the true population, so you're going to have to use the next best thing a lot of times. P hat, Q hat, standard deviation of sample. Okay? So what do we get for Z here?
I have a question. Going off that, why wouldn't you do the standard deviation of the PO if you used those when you did the standard deviation? Because you use the P hat for doing the standard deviation, like you just said, you use 0.5.
Right.
So then why would you?
Why would I use the P hat here?
But why is that the same as P, the standard deviation of P hat? The standard, like.
No, see, this is the standard deviation of all the possible sample proportions. Okay? This is the standard deviation of all the possible sample proportions. And the formula for that is to use the P from the whole population. That's the formula for it. The only reason we put P hat and Q hat in here before is because we used them as our best guess when we didn't know the population proportion. But now we do know it. We assume it. Okay? So save that standard error stuff, square root of P hat, Q hat over N, for when you're doing confidence intervals. And it's your own P hat, really. Here we got this. So, I'm getting like 0.042 over 0.01015, so I'm getting something like 4 standard deviations. What do you get, 4 point, for z-score here?
Yeah, 4.14.
4.14. What do you think? Is this going to be a rare event? We're supposed to make a picture. Here's the picture. Now, remember, we were very picky before that when you make your normal curves, you should show all the different 68, 95, 99, whatever. You don't have to show that anymore. You do, though, have to label your graph and put some of the key elements in it. And there's 2 ways to think about this. You can either set up distribution of all p hat, all the possible sample means, and say that it peaks at 0.5, and the standard deviation is about 0.01. So here at one inflection point there, we've got 0.51. And so we find ourselves way over here with our 0.542. Or you could show me a normal curve and say these are z-scores now, and the standard normal curve is centered at 0, and I have 4 standard deviations. Oh, scale not trying to scale there, but you can see it's going to be really tiny probability. I'll accept either one of these, okay? As long as you label it correctly, so I know what you're talking about. Okay? I think you've been focusing on this a lot, and that's a good idea because it's a little closer to the application. Remember, the normal curve is so you put in your calculator, but actually you can put any of these in your calculator to find p-value on it. Let's do it. Don't shout the answer.
I have a question.
Yes.
For that, how come you label this p hat? There's always using p.
Right. This is all the possible sample proportions. We found one at 0.542. But this whole normal curve is representing all the possible experiments you can do, all the possible samples you can do. And they will cluster around the true population proportion of 0.5.
What does p hat mean?
P hat is the sample proportion.
It's the one portion that you did. And
Right.
the curve is all the possible
Right.
sample proportions you could have gotten.
All possible p hats. And we're just looking at one. And notice, we're not just looking at probability of that one p hat. That would be 0. We look at the probability of getting that p hat or something more extreme, something further away in this direction of our alternative hypothesis, which we stated before was greater than 0.5. So what do you get for this p-value? Let's just tell us. Because we stopped at the 10th.
Yeah.
0.0001.
How do you get that? Just type everything into your
We
calculator.
do the normal CDF, and the z-score is 4.14, and then infinity is your high value.
Normal CDF. And you can just put in 4.14 to infinity.
Yeah.
Like that.
Yeah.
But now you also, see here, I had to memorize what the commands were in the calculator. It's a lot more convenient if you go to the stats menu and just call a normal curve. And you can put in the thing, and you put in all the details. You also have the option at that point too, to put in this mean and the standard deviation from your p-hat distribution. You don't always have to do it in the normal curve. Okay, do see me to practice going over that in the calculator, okay? Sure, there's a lot of different.
Okay, you do equal to p, because here it says less than. But then I thought it was for p value.
Okay, it's only saying less than 0.07 because someone looked this up on a table. That's not the exact value. If you put in 4.14 in your calculator, it probably gives you something with scientific notation. Try it. Okay?
Are we going to state the conclusion then for the last part?
Yeah, let's get to that. State your conclusion. Since the p-value is less than 0.01, it's very small, we reject the null hypothesis. Now that's just the statistical decision. If the p-value is small, you reject the null hypothesis. If the p-value is large, you fail to reject the null hypothesis. But you have to put this into context and explain it. Okay? There is sufficient evidence to show that the proportion of home games won in the MLB is greater than 0.5. And that's what means to reject the null hypothesis. So So in your words, you can state the alternative hypothesis then. Now, sufficient evidence. Does this mean this is absolutely true that the Oakville advantage is greater than 0.5? No, there's a small chance we might have made an error. Now, where does it say we're supposed to enter in?
You're supposed to get through all of
We're
it.
supposed to get through all this.
We got to
Still
where we were
on
supposed to
Right.
end
So
it.
that's why we're just going to continue along with the notes tomorrow.
So we,
Do what homework you can tonight. Chip away at it.
So don't read chapter 21, because that's too difficult.
Oh, I would definitely, I read chapter 21 this morning. It's delightful.
It was delightful.
Delightful.
Should we
You
read it
should-
tonight?
Yes, you should read. Because that will give you.
so are we gonna be doing
Because you'll have more.
warm up on
more
chapter
homework this
21?
morning. So read tonight. Okay? We'll probably do that since probably the reading quiz tomorrow.
Is on chapter.
What we'll do then is go and finish the resource. Then we'll do that.
Yeah.
That would make more sense, right?
Yeah.
Okay. The warm-ups, do I have all the warm-ups? Are these some of them? What are these? Okay, these are the warm-ups? Is this a warm-up?
Yeah.
You're gonna get the warm-up there.
I literally, it's not even like in my brain ever to like
Okay.
think about it.
I'm gonna go to the theater.
Glenn, do you have a class right now?
I'd have to check on my schedule.